the slice selection gradient here. Okay, so I already explained about the slice selection process sequence here, and I explained about the resolving the space information using gradient. So this gradient is called the Dirac gradient because the signals, if the signals comes like this, then after the read the signal, the Fourier transformed signal has the spatial information. But there are some problems here. You can recognize the problem here. Yeah, signal decays very, very fast here, right? Same problem, as I said before. For the slice selection gradient, the excited signal also decays very fast due to the gradient. So in here, the same problem occurs here because Dirac gradient is also very strong field inhomogeneity. So the T2 star is very, very short. Right? So we can not acquire the data for this signal. So how can you solve this problem? The same method can be applied for this gradient. So the compensation gradient is applied before the Dirac gradient like this. Previously, this this compensation gradient displaced the signals. So the displaced signal is compensated by Dirac gradient here. So the compensated signal generates the echo like this, right? So using this gradient, the echo signal is generated, and also data acquisition can be performed in this type here. So during this gradient is applied, data can be read out here. So that's why this gradient is called as Dirac gradient. Okay. So this signal has the echo form because the dismissed signal is regenerated here. So we also this signal as echo signal, and this signal is regenerated by gradient pulse. So we call this signal also gradient echo signal. Spin echo signal is RF echo signal, right? RF echo signal or spin echo signal is generated by 90-degree RF pulse, and the combination of 90-degree RF pulse and 180 RF pulse. RF echo. Okay. RF echo is the spin echo. But gradient echo signal is generated by the gradient compensation. So this echo signal comes from the FID signal. FID signal, echo signal is derived from the FID signals. So there are two echo signals in MR signals: RF echo signal and gradient echo signal. So in here, RF echo means spin echo. Okay? So symbolically, we usually use SE. SE means spin echo. signal frequency is determined by the gradient field. So this is just a modification of ramification, because GR is a magnetic field, right? So the ramification is very, very important basic equation for MRI system. This slide explains the property of MRI signal. As I said before, the readout gradient. Readout gradient generates the echo signals and the time duration of data acquisition time. So, by applying the readout gradient, the signals comes from the object and the data are acquired. And this is the spectrum of MRI signal, data acquired data. So rho x equal rho x comma y dy. That means the acquired data comes from the object in these directions. That means during the gradient is applied, the precession frequencies are the same on the line, right? That means this signal, the acquired data are summed up along the lines. That means the acquired data has the summation of the on the line in the perpendicular direction of applied gradient. So that's why the Fourier transformed signal is the integration in direction of y direction. So we call this data as a projection data at point x. So if this point is at, then the signal strength means that the integration of a signal on the line here. So we call this data as a projection data in x direction. So by applying the readout gradient, we only resolve the position information in readout gradient direction. So in this case, the readout gradient is applied in x direction, and the gx is readout gradient. So gx equal gr. So this slide summarized the previous slides. So for the selected slides here, the readout gradient is applied in x direction. So the magnetic field distributes linearly distributes along the x direction. So the precession frequency is linearly increased in x directions. So and to compensate to generate the echo signal, the compensation gradient is applied before the readout gradient, and according to this compensation gradient, the echo signal is generated at the peak of echo is generated when the area of compensation gradient and the readout gradient is the should be changed. For the small area of compensation gradient, the echo signal generates in the earlier time. For the large area of compensation gradient, the echo signal is generated on late time. So we can control the position of the echo signals. And here, this equation shows the same equation as I explained before. And this should. Yeah, this is inner product. This is actually this is the vector. Generally, position. If the position has the vector form, then the product is the inner product. For the scalar, just the scalar case, omega equal gamma g x x. This is just a simple scalar product. Let's assume that the one voxel here, one voxel here, and the spin density is represented by log x at the x position. Then the signal has the frequency of omega x, which is represented by this equation, right? So the signal comes from this voxel can be have an equation of like this, and the acquired signal has the mathematical form of like this, because the spin density becomes the line integral of the signal comes has the same frequencies on the line, so the detected signal has the integration in sorry, it should be not x, it should be y. Rho x. Sorry, this is the dx, because the echo signal comes from all these objects, this all image slices. So the echo signal has the integration form in x direction, and the rho x is the integration form rho x comma y dy. So that means the projection data in y direction. So the acquired signal has the form like this. So this is also 1D Fourier transform equation, right? Yes. So the rho x can be obtained by inverse Fourier transform of st. So this is the rho x, and this rho x is obtained by inverse Fourier form of echo signals here. Oh, this projection data is shown here. So I explained the first diagram, this part. Okay. Slice selection is performed by RF pulse and gradient, slice selection gradient. This is the compensation gradient. And the echo signal is read out using this without gradient, and this is gradient is the spatial information can be resolved by the remained axis from the slice selection direction and the reduct gradient direction. So from this slide, the remained direction is in y direction, right? So because this echo signal has the space information only in x directions. So we have to resolve the space information in y direction using phase encoding direction. I just missed one explain here. Reduct gradient is also called as a frequency encoding gradient. Frequency encoding gradient means the spatial information is encoded by frequency. So the frequency encoding is the same terminology as reduct gradient. So phase encoding, GP means the phase encoding gradient. So you can infer the meaning of phase encoding. The space information is encoded by phase information. So phase encoding, even though the space information is encoded by phase, the principle is the same because this method also used Fourier transform. Okay, let me see. In the Fourier transform equation, we used j omega t, right? And omega t is phase, right? So using the reduct gradient or frequency encoding gradient, spatial information is encoded by the frequency omega, right? But for the phase encoding gradient, the space information is encoded by omega t. That means the pi. So that's why I said that the principle is the same because they use the Fourier transform theory, right? So this phase encoding gradient is used to encode this phase, and the phase is calculated by the integration of frequency in time domain, right? Okay. So phase is the area of frequency graph. So the area of this gradient part is determined the phase of here. So that's how to encode the phase using this gradient parts. So I will explain about that. So what time is it now? 4? Okay. Yeah. I think, okay, I will explain. I have enough time, I think. So, let's assume that we would like to encode the space information along the axis P. P-axis can be replaced by X or Y or G according to the slice orientation. And when you apply the phase encoding gradient like this, then the spins, the speed of rotation, precession of spins are